everyone hear me? Right, so thanks Hamza, and thanks to the organizer. So today I'm going to talk about sequential decision making under uncertainty. The idea is that you're going to have to make decisions one by one in order to optimize some sort of criteria of all those decisions, and the idea is that you don't really know everything about the environment. So I'm going to give a bunch of examples. First, I should say that this is joint work with my collaborator Vianney Perchet, and that we'll have this at NIPS this year. Okay, so one of the applications of what I'm going to talk about is the very famous example of what's called multi-arm bandit. The idea is that when you enter a casino, you have different slot machines that are called one-arm bandits, hence the name of the problem. And each of them has a different distribution for their reward. So the distribution is called mu I, and everyone has a different mean, right? So there's some slot machines that are better than other slot machines. There's a sequential aspect to this problem. At every round, you can choose to play one of the slot machines, not many of them. And there's a bandit feedback. So the idea is that you only observe one feedback. You don't observe what would have happened if you had played any other machine. You observe xt that's drawn from the distribution that corresponds to the pi t that you've chosen. Right? Pi t is your policy, your action. And it has mean mu of pi t. The objective here is to get as much money as possible, like in a lot of problems. To maximize your reward or your expected reward, and there's the notion of a regret, right? So you compare what you have gotten to what you could have gotten if you knew in advance which was the best machine. Right, so the reward would be just the sum of the xt's, the sum of each individual reward that you get. The expected reward would be the sum of their means, right? So the sum of mu of pi t, where pi t is the action that you've chosen, which you can rewrite as a sum of mu I times the number of times you've played the action I. So this will be a frequent notation here. Ti is the number of times you've chosen the slot machine I. And if you subtract capital T times mu star, the highest mean, then you can compare this to the best possible action. Okay, so there's definitely an exploitation point of view in this problem. The idea is that you want to play the best machine. So you want to play the machine that you estimate right now as better, meaning that it has a higher mean reward. There's also an exploration point of view, because in order to be able to exploit this good machine, you need to know which one is the best machine, and so you need to have good estimates. Right? You need to have good estimates mu at I of each mean reward. So in your mind, above each machine, you have some estimate of the mean reward, and the idea is that maybe you want to play the one with the best estimate. Here you can see already that there's an exploitation trade-off, right? The classical statistics point of view maybe here would be that you play uniformly and infinitely every slot machine, infinitely many times every slot machine, and so you get estimates that converge to the true values, and at the end you only play the best one. The issue here, of course, is that you don't have infinitely many coins, and so you need to balance what you learn about the slot machines and the fact that you want to exploit them at the same time. And this can be seen as a stochastic optimization problem. You're trying to maximize a function of capital T1 to capital Tk, right? So this is a vector number of times you've played each machine with some unknown mu I, right? So here this is this function. So this has, of course, many other applications than getting kicked out of casinos. It comes initially from medical experiments. So the idea is that for every patient, you have a range of possible treatments, and you want to find the best treatment, but you also want to save as many patients as possible. So you're trying sequentially to get information about every treatment, but also to try and give the best treatment every time. It also comes up in advertisement. The idea is that every time that a customer comes on your website, you want to find the ad that has the best chance of your customer clicking on it, but also you need to display kind of all the ads if you want to estimate these chances. and also artificial intelligence in games. Okay, because every time you need to play an action and you're trying to win a game. And so in a problem that you can see like this, there's one best action, and you want to play this action all the time. But you can think of many other situations where actually you need to make a lot of decisions sequentially in time, and there's not one best action, there's one mix, one best mix of actions. Right? So here, this is writing this in a stochastic optimization point of view. So you have this function that's a scalar product between the vector mu and the vector x. You look at the variable x on the simplex, right? So here, this is what happens if you only play the first slot machine. Here, if you play only the second slot machine, and here, if you play only the third slot machine. You can see that the reward is going to be this function applied at the point of proportion, proportion that you've played each action. So you can see it as a stochastic optimization problem where you have an unknown linear form. The linear form is going to be minimized at a corner of the simplex, and that's where the best arm is. The idea is you don't know this vector, of course, otherwise this problem would be very easy. But you have a feedback on the vector that's tied to the variable where you're at currently. So if you call pt this vector of proportion, that's in the simplex by definition, if t1 is very large, you have a lot of information about mu1. If tk is very large, you have a lot of information about mu k. But in general, your feedback on the function and on the corresponding parameter is tied to this variable. And here there's an optimum p star at e star, which is a corner, right? Vector of the basis. Some zeros everywhere and 1, 1 at the star coefficient. Okay, so this is very simple setting. There's one best action. The function is very simple on this simplex. But as I said, there's many concrete situations where the function that you're trying to optimize is not like this at all. Okay, so you can think of the situation of someone who enters a supermarket and can buy, let's say on this figure, 3 goods, right? So in general, K goods. So this person can buy bread, wine, and cheese. And of course, the best thing is not to buy only bread, only wine, or only cheese. It's to buy some optimal proportion of these 3 things, right? And every person is different. Every person has different preferences. And so every person is going to have a different utility function like this. So if you have a basket of K goods and you're trying to maximize this utility function, so this is a very simple utility function. It can be written like this. It's equivalent to having a loss function of this form that's convex in all the variables. Initially, you don't know these coefficients beta I that describe your utility function. But every time you put something in your basket, you can kind of look at your basket and get an estimate of this beta I. This is an estimate of how much more happy you are with this new item in your basket. Right? This is something that people can usually describe. You give them something and you tell them, are you more happy? Are you less happy? Are you very much, you much more happy or not? This is something that they can give you. They can't usually give you their beta I's. And so if you're playing this game, if you're entering the supermarket and every time putting a good in your basket and looking at this utility function, you're getting more and more information about the unknown beta. You're getting more and more information about this function. And so here again, the feedback on beta is tied to this variable. The optimum here depends on the betas. It will be in general in the center of the simplex. And here you can have the same sort of game where you try at the same time to estimate the function, so to estimate the betas, and to optimize it at the same time, because you want to get out of the supermarket with the best possible basket. Okay, and there's many other problems of this type. So if you have an unknown vector theta and you have k different sources for the coefficients of this vector, and they each have different variances. First year undergraduate problem would be to ask students what are the deviations of your estimate for the vector given all of these quantities. They would tell you if they're good students, that it's the sum of the sigma I square divided by the number of times you've sampled each coefficient. And if you have a second-year student, you can ask them to optimize this, and they'll find that the optimum of this function is where the Ti must be proportional to the sigma I. So if there's a source that's very uncertain, it means you must sample a lot from this source, because essentially you want uniform uncertainty across all the coefficients. Right? So if you're trying to do some, sequential experiment design like this, you want to estimate the sigma I square and at the same time to find the optimal Pi. And so you might have a function that looks like this. Right? So very generally, you can say that you have a stochastic optimization problem of L on the simplex. It has some unknown parameter. You're getting feedback on the parameter that's tied to the variable. And the optimum is at P star somewhere in the simplex, and your error, your optimization error, is measured like this. Right? It's non-negative, and it's equal to 0 if you're at the optimum. Okay, so in a more formal setting, this means you have an unknown convex function L. At each round, you choose some action in one of these k actions, and you observe a vector g hat t that's a proxy of the gradient. Right? So it describes how the function varies, and each coefficient of this gradient has a precision that depends on the number of times you've played each action. Right? So this is generalizing what you have in the parametric case, where you have a mu I or a beta I or a sigma I squared to estimate, and your precision of this, precision of the parameter, precision of the gradient, depends on the number of times you've played each action. So you're choosing the actions in order to minimize this, and the performance of any policy is measured like this. Are there any questions so far? Okay. So now the question is, how do we address these types of problems, and how are they different compared to other problems that have been looked at before? Right, so the idea here is that this is a new problem because it's different from Bandit's in the sense that the loss is not cumulative. You're not saying, okay, I'm going to look at a sum of individual losses for each action. You're saying that you look at a global loss that's applied to the mean of the actions, right? To the vector of proportions that you've played each action. There's no individual best action in general, but some optimal best mix strategy. It's also different from stochastic optimization because you have a constraint on the variable that you choose. Right? So the idea, if you go back to the simplex that I had, is that you can't at each round just select where the variable is going to be and where you want it to be. You can choose a corner at each round, and your variable is going to do a small step in this direction. That's the only control you have over the variable. So it's not chosen freely in the domain. And also the gradient feedback, so the information that you get from the function, is tied to your action. It's not some independent stochastic gradient, just like it would be in general in stochastic optimization. Right, so there's existing work a little bit in this line of work in a restricted case, but in general, it's with non-convex logs and linear bandits. So here we've generalized this. The idea is that this is a little bit like you have the same rules as a bandit problem and the end game of stochastic optimization. Yeah.
So I just wanted to, so if you go back, I mean,
yep.
So your variables were this TIs, which is the number of times you use something. So but I mean, when you look at this as being your variables, where does the problem doesn't become online anymore? I mean, you can, because so if your variables are just the number of times you use this, I mean, you could use T1, I mean, ARM1 first for T1 times and T2 and so on. So
you could do it like this, but the idea is that you would maybe, I mean, if you play the first action T1 times, and the best thing was to never play this action, then you've wasted a lot of times playing this action, and your variable has been damaged.
Yes,
it's going to be damaged indefinitely.
Yeah, but I mean, by formulating the problem in terms of these variables, I mean, this is what I quite don't get. Is, I mean, you
okay, so this is Ti of little t.
Okay.
This is the number of times you've played this action so far.
Oh, okay.
Sorry.
So it
Yeah. It depends. Oh, it has an online component.
Okay.
Yeah, I cleaned up a bit the equations, but yeah.
Sure.
Ti of little t. So it depends on the number of times you've played it so far.
Okay.
Yeah. Sorry if that wasn't clear. Okay, so now the natural question is, how do you try and minimize this? Okay, so the one thing that you can first do in this problem is to just write the dynamic that's imposed on this variable, which means, what happens when you're at the point pt and you choose the next action in one of the corners. So then you can have a dynamic of this form, right? pt plus 1 is just going to be a linear convex combination of pt and the new corner that you've chosen. This just comes from writing these equations. And this means that this is the same thing as being at pt and doing a step that's a little bit in the direction of the corner. So here you have an example like this. You have a point. So this is going to be more general, but if you have a point pt here and you choose this action, you do a bit of a step in this direction. Okay, so this line here is just writing the rules of the game, writing the dynamics of the problem. So this is similar to a gradient type update. So people who've done things like gradient descent or other first order methods, you get a lot of equations that look like this. pt plus 1 is equal to pt plus a small thing that depends on the function. You're trying to go into the right direction, trying to minimize this convex function. In particular, there's an algorithm that's been developed in the 50s for constraint optimization problem on a convex domain C. The idea of this optimization algorithm is that you shouldn't go into the negative direction of the gradient like gradient descent would do. You should use a lot the information that you have about the domain you're in and solving this optimization problem. Right? So finding the point in the convex set that is at most in the direction of the negative gradient. So this is this point here. And then you do a linear combination of this extreme point and the point you're at right now. So it's kind of stepping in the direction of an extreme point that's pretty much guided by the negative gradient. And so here, if our loss function were known, and if the gradient were known as well, we could just take the next action to be equal to that, to be the point where the scalar product between the gradient and u is minimized, or the point that's the most in the direction of minus the gradient, and we will solve our problem. Right? So our problem would be, in some sense, easy from an optimization point of view if the function were known. Right? So this is what I write here. If this is known, you apply this algorithm with this step size. This is not something you can choose again. This is something that comes from the dynamics of the problem. And you get a guarantee that for a C-smooth convex function, this is going to decrease like log t over t. Okay, so if t becomes very large, you have good guarantees. If you have an unknown gradient, because you have an unknown function, the most naive idea is to use the proxy that you have for the gradient and to just plug it into the algorithm instead. So you put the stochastic gradient here. This means that because you have a stochastic vector, so a proxy for the vector, you're going to go into the direction that's most in the, you're going to take the corner that's most in the direction of negative this stochastic gradient. But this can be the wrong corner, right? So if your errors point in this, make the gradient point in this direction, then you're going to choose this corner instead. So you have some errors when you do something like this. And in particular, so even for the first problem that I introduced in the case where these are linear functions, the case of multi-arm bandits, this is known to be problematic. Because the idea when you're doing something like this is that you're always choosing the slot machine that has the best estimate. And if in the beginning you played all the machines once, if the best machine you were very unlucky and got a very bad reward, this means that you're never going to play it again. Which means that you're always going to select suboptimal machines. And so this can be very problematic, and you really want to prevent yourself from doing something like this. So the usual fix in this case is to correct for the uncertainty. that you have in mind not only an estimate for each machine, but also a confidence region for it. Which means that if you play a machine only once in the beginning and you have a very bad reward, then you'll know that you have a very bad estimate, but you'll know also that there's a lot of uncertainty on that, and so that maybe the actual reward is in a big region around this estimate. And so the way to do this, in the case where you have a constant gradient, when you have something that's just a vector that doesn't depend on the position in the simplex, is to correct by the size of the uncertainty. If you have a very bad uncertainty, you're gonna play this machine more times because you want to get a better estimate. This is how you kind of solve this problem of correcting for exploration. You don't want to do too much exploitation, you want to correct for exploration. And so here this is the size of a valid confidence region of order of this size. Okay, and so here, this is what we've just done. We've generalized this idea. So in the multi-arm bandit, this is called the upper confidence bounds or UCB algorithm, and we've generalized it to the Frank-Wolf algorithm. We've said, going back to the previous slide, if you are in the linear case, the UCB algorithm consists just of taking the best estimate corrected by some size of the interval, which is equivalent to doing this. We're going to generalize this by putting the proxy of the gradient minus the size of the confidence intervals, which is exactly what we do. So we observe a noisy gradient g hat, so a noisy version of this. We correct for the uncertainty because we know how many times we've played each action so far, so we know by how much we can correct. And then we select the action that minimizes this criteria. This will update this naturally. Right? So I'm going to go back to the picture that I had. The idea is that we have a stochastic gradient, but we put a box around the stochastic gradient because we know the confidence that we have on each interval. Maybe it will be very small for some variables and very large for some other variables. And then we solve the problem with the worst case gradient in this box. Okay, this is how we correct for the fact that we need to do some exploration. So each coefficient is penalized by uncertainty. This promotes exploration. This runs in very fast time, so if you omit gradient computations, this is pretty much as fast as an algorithm like this can run. It's in linear time in t. You don't need to make very complicated computations at each round. And the proof elements that I'm not going to really present here are really also nice because it really comes from the two theories that we're bringing together here. So you first analyze this algorithm as you do originally in convex optimization if you didn't have any error. And then you control the error as it's done in bandit theory for the usual very simple multi-armed bandit problems. So the idea is that when you adapt the proof of convergence in optimization for known gradients, you get the usual optimization term and an error of choice of the corner. If you know the gradients, then these are always negative. But in general, these could be positive, right? So this comes from the error and can be seen as your statistical error. So altogether, when you analyze this algorithm with stochastic errors, you can get a slow rate by controlling this, by doing some sort of averaging argument, and you get that this decreases like square root of k over t, which is much worse than something in log t over t, especially when t is very large, which is what you have when you know the function. So in this case, this is in some sense the cost of not knowing the function. This is the statistical error that you have to pay because of that. We know that in the linear case, this matches the known results that are obtained for this problem up to some terms. And again, up to some terms, there is a matching lower bound, which says that essentially even for linear functions, this result is optimal if you don't know the function. This is the price that you have to pay that comes from the statistical error. Okay. It's possible to do some improvements on this result if you make additional assumptions on the loss function. So in particular, if you make an assumption that the function will be minimized at a corner, and negative of the gradient goes really in the direction of a cone around this corner, then you can say that even small imprecisions on this gradient will not make you think that another corner is optimal instead of this one. Right? The idea is as soon as the gradient starts to cross this line, then this other point is optimal. And so if you think, if your estimate of the gradient can be in a big ball around this, and this is close to a boundary, then there's a chance that you make a mistake and that you think that another corner is optimal. And so you can incorporate these ideas to improve the rate, to say that if you have some big gaps between the values of the coefficients, so the values of these gaps describe the distance to the corner, this is the geometric interpretation, you can get a fast rate that depends on these quantities. So if these quantities go to 0, this constant explodes and it's not interesting anymore. But if it's bounded away from 0, if you know that your true vector is bounded away from the boundaries, then this works out well. And this is possible, and you can generalize this to any function that's minimized in the corner. Now you do now you look at the gaps on the coefficients of the gradient, and the same type of reasoning will give you the same type of result. So you get also a fast rate that depends on the gap at each point. So the KKT conditions and optimality conditions in general in optimization would already give you that these are non-negative, which is just like saying that the gradient would be in this corner, but the delta I is described how much into this corner this gradient is. Right? And so this should be a minus L, minus gradient of L, and you can see that when the function changes and the gradient comes closer to the boundary, uncertainty will make you hesitate between these corners more and more. But if you have a very nice situation like this, uncertainty will be less damaging. That's what this describes here. Okay, so this is a situation where we can get faster rates when we are in a corner. There's another situation where we can get faster rates by adding structure in the case where we want mixed strategies, so where we want an optimal point to be in the inside of the simplex. And in this case, what we can consider is mu strongly convex functions. So these are essentially functions that look like quadratic functions around the minimum. They're not flat around the minimum, and there's no region where they're flat. They look parabolic everywhere. Right? So this is the linear term of a convex function. And so if it's equal to this, it's linear. If it's close to this, it's really flat. This is saying that the function is above its first order approximation. If you have something like this that's satisfied and the true minimum is far away from the boundary in a way that you can measure, then this is a classical hypothesis in stochastic optimization, in particular in Frank-Wolf. It's not something that always exploitable in bandit problems, but here it will help. So again, not going so much into details, but there's technical results that help us here and that tell us that we can improve these results. Right, so the worst case results that we had when the function was just moved was when the function was very flat, when it was a linear function. Here what we're saying is that if the function is bounded below by a function that kind of grows like this quadratically, then we can again improve these rates. The idea is that if your function is really flat, it's again easy to hesitate between 2 points being optimal. Whereas if it's really strongly convex in this sense, then it's harder to hesitate. These are the same ideas saying that, let's say in a classical statistical problem, the Fisher information will drive the hardness of a statistical problem. The Fisher information describes the curvature of the function that you're trying to minimize. Okay, so here we are in a nice case and we can get, again, a fast rate. So the summary of the positive results that we have for this is that if you have a slow rate and your function is only convex, and in the case where the function is only convex smooth, it's going to look like this. You're going to have a square root of k over t. You can get a faster rate if you make assumptions, so a corner condition saying either that one of the action is clearly better than the other, or the completely inverse case, a situation where you have strong convexity and the minimum that's in the interior, So you have a mixed strategy that's the best, and your function, your loss function clearly says that this one is much better. You can also get faster rates. Some remarks is that these results are all optimal. So over this class of functions, we can always establish matching lower bounds that say that you can find a worst case set of functions over which all algorithms will perform like this. In both cases, so in all the cases, so either C-smooth or with gaps or with strong convexity. Okay, do you have a question or?
No.
Okay, so this is just my last slide, if this was what you were concerned about. So here we have a new model that links stochastic optimization and bandit problems. These types of ideas, these types of at least questions have been looked at a bit separately in both communities, so kind of bringing these two together. Of course, this is a natural playground for various applications. So this can be, you know, you're trying to buy a portfolio, a basket of goods that must be diverse and satisfy some, optimize some criteria that are still unknown, so that you're learning at every round. This can be also, you know, sending aid to different parts of the world with some uncertainty about how much aid is needed in different places. And what we liked also is that the solution that we brought also brought ideas together from the two domains. And the algorithm is very simple and doesn't need to know anything about the function. This is what adaptive means. We have plenty of open questions for this, and I'm very happy to talk to you if you have any more questions about that. Thanks a lot.
Any questions for Quentin? Yes.
So you had this, thinking about the structure of the problem, it's basically a setup where you can control the errors in the gradient estimates based on the decisions you've made in the
Yes.
process, right? So in your setup, there was a specific way in which that shows up, but you could think of a more general model where, like,
Yep.
I can make some decision that costs some computation,
Yep.
but it'll improve my gradient estimate.
Yeah, absolutely. So in the paper, let me go back. So in the paper, this is a general function of alpha of Ti that can incorporate all these things you're describing. And then we have all our results that depend on that. And it's just that the most common choice for a function like this is something over the 1 over square root of Ti, where there's just a statistical cost. And so this is why everything that I presented here is of this form. But you can absolutely generalize it. And this is what we've done in the paper.
And rather than just counting it in terms of time steps, you could count that, like, there could be a cost of a process that I run at time t.
Yes. So this is in the open questions that I have at the end, I think. More complicated feedbacks. So the quality of your feedback depends in a more complicated way on the set of actions that you've taken so far. So this can incorporate some things that you're describing, but what we're also interested in is situations where you're trying to design experiments online. So the result I presented was a very simple case where you get information about one coefficient every time. But if you have something more complicated than this, when you have a linear combination of each measurements, each with its different variants, then you need to understand something like this. And this is something that we don't understand so far, but this is the natural next step in this.
Yeah, I mean, so we've looked at multi-arm bandits at Cantab, and there the application is with execution algorithms. So we have many different algorithms to execute orders. Which one should we pick to execute? So we end up in this interesting place where clearly we can measure the performance of each of those, and we observe some more than others. So maybe we want to use the cheapest execution, but also there's some value in information. So we want to learn about things we haven't observed. So it's very much this situation. And so one of the things that I wonder about is an interesting generalization is to allow those means to vary through time. So of course they vary because you're estimating them, but also maybe they're not stationary.
Yes.
So one way you could do that is if you hadn't observed something for quite a long time, your uncertainty on that estimate starts to grow again.
Yes.
That would be a natural thing because it's still your best estimate, but actually it could have changed.
Yes,
Is this something that would cleanly...
I think this is something that's been looked at already. So don't remember the exact term, but there's multi-arm bandits with varying means, but there's also something that's called contextual bandits, where if you have side information, if you have side information xt, the mean of each slot machine, or the reward of each algorithm, is a function that depends on xt. And so this means that in some situations, one algorithm will be the best, and other situations another algorithm will be the best, because these functions can look like that. So then you have to not only estimate one mean, but k means, but estimate k functions. And this is also complicated, but there's a big theory on that. Yeah. But again, so this is all in the multi-arm bandit case, in the case where there's always one best one and you're trying to pick the best one. Here what we're trying to do is maybe a situation where you're trying to diversify things a little bit, and so you don't want to play, if you play only one, this means you're only, I don't know, buying the same sort of portfolio at every round. This means if something goes bad, it goes horribly bad, whereas if you've diversified things a bit more, then maybe this can be better. I don't know.
Yeah, I mean, for us, we're comfortable with just picking one for
Okay.
an individual
Yeah.
request. There are many reasons why there's an order to be executed and you should only use one algorithm to do that.
Yes, yes.
So, but generalizing in other ways is certainly of interest.
If there are no more questions, then let's thank Quentin again.